So
they're lost at this point.
Just want to give a little introduction to Scott. Okay, so it's my pleasure today to introduce Scott Hayes, my honors student, and his project, which you need to use my cheat sheet on this. Basically, it's the design of a ThinSat-based composite boom deployment system. The work is part of a larger project that was initiated by Colonel Blandino in the ME department, and that is in cooperation with NASA, Virginia Space, and Virginia Tech. And the purpose of that project is to develop these high-performance composite booms, okay, in support of solar sail technology or solar sail propelled vehicles. It's a really interesting and far-reaching program of which Scott will have a particular piece, and it's been my privilege to work with him on that. And I really look forward to seeing how this technology and his designs come to fruition, hopefully in some kind of future launch. For those of you who don't know Scott, which is about 3 of you in this whole room, he's a really bright guy. I can speak to that. I've had him in many classes now. Has a fanatical workout schedule, which is impressive in and of itself. And then he is, of course, the 1st Battalion Commander, so go figure. All of that is pretty impressive when you consider how much time that an honors project actually takes. He's done that well, and he's done it with a sense of humor, which is probably more than I would muster in that area. So, kudos to Scott on that. Okay, before I give the floor over to him, I did just want to reach out, though, and thank all the people that helped him on this project, in particular, the Honors Committee. Colonel Joe Blandino here, who was very instrumental in getting this project going. And of course, the ME staff, okay, so our Charlene Graves, Mike Cullen, Marco Floyd, all these people have been instrumental in making this project happen. So that said, thanks to all of those people, and I'm going to give it over to you.
Thank you for that introduction, Colonel Sullivan. To all of you in the crowd, thank you for coming. As previously stated, I am Scott Hayes, as many of you know, and today I'm going to be presenting to you my senior honors thesis. It's entitled Development of a Deployable and Retractable ThinSat Boom. So, quick overview of what we're going to be talking about today. Starting at the top, the first topic we got to get into is what is a ThinSat and why are they important? Then we're going to move into the ThinSat initiative, the goals of this project, the design process that we took. We're going to go over the final statistics and open up the floor for questions. So first off, we have to talk about what is a ThinSat. So before ThinSats were even a thing, the first generation were called CubeSats, and that's the picture that you see up at the top of the slide. And those were 10 centimeter by 10 centimeter by 10 centimeter cubes that were developed in the late 90s by Cal Poly in Stanford. The main mission of these was to promote and develop skills that were necessary for designing, manufacturing, and testing of small satellites, and they were intended for what's called LEO, or low Earth orbit. And so what the goal of these was, as you can see in the picture, there's a circuit board at the top. They were basically setting them up and using them to perform scientific research functions that we can't do on Earth. And the reason is because LEO, low Earth orbit, there's zero gravity situations. So the vast majority of early CubeSats were designed and deployed by academic bodies, such as, like I said, Cal Poly and Stanford, but they were still incredibly expensive. So only the bigger schools really got a chance to use them. So then in 2009, Hank Voss, a designer with Twig Aerospace, he wanted to make the CubeSat more accessible for the smaller size schools, even high schools. So what he did was he basically took the CubeSat and chopped it into 6 even parts. So that's what you see right here. So like I said, this is about 10 centimeters by 10 centimeters by 10. This is 1/6 of that total volume. And he called them pocket cubes. And the only problem with the pocket cubes was because of their really small size, it was very hard for people who weren't professionals, so people who were in high school and college, the exact people he was looking for, to put things into them because they just didn't have as much experience as people at maybe in grad school, people who had been doing this for a living. So he went back to the drawing board, and in 2016, he was looking at a CubeSat, and instead of cutting it into cubes like he did before, he thought, well, what if we sliced it like a loaf of bread? And then the ThinSat was born. So, interesting quote is, we always talk about the best things since sliced bread, but maybe in 100 years from now, when bread is, we don't eat anymore, we'll drink things out of tubes, maybe we'll have the best things since sliced ThinSats. But anyway, we digress. So you're probably wondering, why is this all important? Why is it really important if we are using this type of technology? And the answer to that question is TRLs. TRL stands for Technology Readiness Levels. So these were developed by NASA, and basically what the point of them is whenever we have any project that has to do with flight, you start at TRL 1, which for those of you who can't read it, it says basic principles observed and reported, and then we're going all the way up. We're trying to get all the way up to TRL 9, which is actual system is flight proven through successful mission operations. This is like basically, for those of you who might be pilots, like a pre-flight checklist. You're taking your original design, you're making it go through each one of these checks, and eventually you want to get it to TRL 9, so that way, okay, we can use this, we know it works, we've proven it, let's hit the ground. So, by putting technology into the space environment, we can jump from TRL level to TRL level. So in our case, what we're doing is we're looking at the deployment system for this boom. We're trying to take it from somewhere around like a TRL 4, which says component and or breadboard validation in laboratory environment. So like that makes sense, we're working in a lab, and move it hopefully up to something like TRL 7, which is system prototype demonstrated in a space environment. So like if we get it to go on a true space mission, that's where it would strap. Another really interesting thing is this whole TRL system is awesome for saving money and lowering risks. If you, like, one of the things that this boom technology may one day be used for, like Colonel Sullivan mentioned earlier, is something like a solar sail, right? But the problem is, if we were just to build a solar sail off what we know about, based off how this operates in gravity and put it up in space, we probably end up wasting a lot of money because we had sent it up there, things wouldn't work the way that we wanted to, we had to bring it back down, make changes, so forth and so on. By using these smaller test sites like CubeSats, we're able to save money, improve the process in smaller steps, so that way once we finally build a big project, we can have a much more certainty that it will work. And also it shortens development time. So I'm going to talk about a little bit about the ThinSat initiative. So you're all probably wondering, okay, Scott, like I get what ThinSats are, I don't understand what TRLs are, but how'd you get your hands on it? Like, were you just talking to somebody? No. So as I mentioned before, Twig Aerospace and Virginia Space, they had this idea for ThinSats, and they wanted it to be made more accessible for colleges that weren't as big as some of the other ones. So they got in touch with Virginia Tech. Virginia Tech got in touch with Colonel Blandino, as stated before, and Colonel Blandino got in touch with me, and that's how we got here to working on this project. So basically, the partnership between Twig and Virginia Tech, the process that they're trying to do is they're trying to prove that ThinSat, which is 6T, so let me back up for a second. So when I say 6T, this is 1T of a ThinSat. This is one portion of it. 6T just means 6 of them stacked on top of each other. We're trying to prove that a development of a 6T of this is just as economical as producing a 1U. So 1U for a CubeSat is that 10 by 10 by 10 dimension that I mentioned earlier. So in the end, they would be just about the same dimension, but we're trying to prove conceptually that they would be just about the same or better on the ThinSat side. So our goals for this specific project. Number one, we had to deploy and retract a composite boom from a 6T ThinSat, as I mentioned before. So the boom itself that we have, and I brought it in today, this is 2 meters long, wrapped all the way up. And the goal that they had was they wanted to be completely deployed in 60 seconds and then completely retracted in 60 seconds. And all we needed for a duty cycle was 10 deployments and retracted. So for those of you who are working on ME 300 level classes, this is pretty short duty cycle. We're not going for millions, trying to test this out for long periods of time. This is short and quick. Let's see what type of information we can get. The total mass of the project, so outside of the ThinSat border that I just showed you, it had to be 400 grams or less. And then the motor voltage, because of the size of the batteries that were going to be used on this mission, the motor voltage had to be less than 5 volts. So I'm going to dive into the design process that we took. So a quick overview of the design process. So the first thing we had to do was torque characterization. I'll really start to show you something on that. Then once we found out how much torque we needed for this project, we chose a motor, we designed a powered spool, and then something that is going to come up talking about is called the blooming prevention system. And we had 3 designs for that. So first and foremost, torque test. So with this type of project, the one thing that we had to get before we could go anywhere was the testing of how much torque it took to wind up this boom. So there were 3 options that we could have gone with. We either gone with the experimental method, which is what's displayed in front of you. So and I'll dive into that in just a quick second. We either go with analytical, which is using like a solid solid program that evaluates it, or use what's called an inline. So an inline, and that's basically like using sensors and stuff like that to get the torque. So we decided to go with the experimental because the analytical, we're asking it to almost look at how this stuff behaves randomly. And if you ask a computer program to evaluate how something behaves randomly, usually doesn't end well for you. And then the reason we didn't use the inline is because it was going to cost about $4,000, and as somebody who still uses coupons, that's not really in my budget. So we decided that we were just going to go with the experimental method. How we did this, so I'm going to turn this to the side for a quick second so everyone can see. We basically built this boom. We have a certain amount of length sticking out, and then when you remove this, you place a weight on this end right here, and then you measure the distance from the weight to the center. And that, because of, for all of you ME majors, units, that's force times distance that gives us a moment, or in this case, a torque. So that, if you look at the graph that we got right here, one thing that you will notice, it doesn't go completely to 2 meters and it doesn't go completely to 0. The reason is because you still have to have a small amount of it on the spool. But when it was completely or almost completely unwound, that's when we got our lowest torque. And as we wound up, we kept getting higher and higher torques, which makes sense. Like the more that you got on there, the harder it is to turn. Kind of like with a water hose outside. As you get to the end, you really have to put in effort to finish winding it all the way up. And then also, quick thing, this right here is the cross section of the carbon fiber tape that we were talking about, of the boom. It's got really interesting properties. When it's wound up like this, as you can see, it lays flat, but as it comes out, it's got what's called a lenticular cross section. So that's what it looks like, and it has really interesting properties. It's a lot more stiff in this than it is when it's wound up. So, all right. So, like I mentioned before, we had some specifications that were brought to us by Virginia Tech. The first one was we had to do 9 full revolutions in 60 seconds. So, for those of you who were keeping up with us, 9 full revolutions is how much it took to wind this completely up, and then 60 Newton meters of torque. So let me back up a quick second. So if you look on the graph, the highest amount of torque we had was about 55. So for safety, we just rounded up to 60 as the amount of torque that we were going to have to put into the spool to get it to wind up. So after doing some reading, we selected a motor that we thought would work. We chose 50-to-1 gearbox ratio, and it had 70% efficiency. With these givens and assumptions, we found a motor with a ratio of 180 steps per second that would fit our needs. So, and that motor was the Fallhaber AM 1524 0250 motor. So, in case you're wondering, Fallhaber is a Swiss company. Swiss makes stuff other than knives, apparently. Found that out with this project. But so, if you look across the bottom, it says steps per second. So that black line, that vertical line, is where just about we tried to find the 180. So if you follow that up, you notice it says 1 times nominal voltage. The voltage for this motor is 3.5 volts. So we were coming in underneath that 5 volts that we were told we had to cap it at. And it comes in at just about 3.4, the torque on that side is 3.4 millinewton meters. Yeah, so like I just said, the given torque from the Fallhaber tables tells us the motor torque value of 3.4 millinewton meters. And with that 70% efficiency and that 50-to-1 gearbox ratio, the torque to the spool would actually be 119 millinewton meters, which is almost double what we needed. So we got plenty of torque. And so that satisfies the requirement in that aspect. So the next up was the spool, right? So when you're dealing with something that is this small, like I said, 6 of these is just going to be about this space, this big. Space is at a premium, right? Like we really don't have space to be adding extra things. So our design thought process was, okay, what if we were able to put the motor on the inside of the spool? So that's what we did. So we placed it inside the spool. Also, one thing that was really cool is we were able to utilize ultra slim K-Don bearings. So these bearings have the balls on the inside of the bearings have a diameter of 1/8 inch, which is incredibly small. And the total mass of the spool, the motor, and all the attachments to this part was 115.64 grams. And that's pretty incredible if you think about it, because your average apple weighs about 100 grams, so that just gives you a comparison. Like this whole thing, self-driven, all that stuff, is basically the same weight as an apple. Also, we're going to use this spool design with future iterations, so this stays constant. So I've got a little exploded view so you can see what I'm talking about. The motor itself goes in here, and then we've got the bearings. We've got bearings on both sides. This right here transmits the motor torque to the spool, and then also it screws into the edge of the ThinSat. So then we started running into a different problem. So as you can probably see from wherever back you are, however far back you are, if we start to let this go, it doesn't want to stick tight to the spool, right? It starts to come off. It's not like a tape measure where it stays tight the entire time. It likes to come off. So that's obviously a problem when you're working with something that's winding up and then releasing, because if you don't have it tight, then you're basically just going to be running your motor. It might damage the insides. So we had to come up with some sort of blooming prevention system. Now these shown right before you are 3 models that were used in previous years, but they were not designed for such a small handling unit as what we've got in front of you. Like this one on the far side was built for it was for a 3U CubeSat. So again, we're dealing with this much space. They had just about this much space, so it's much bigger than what we got, and that took up pretty much the entire thing. This one as well was just incredibly complex, and since we were trying to keep it under 400 grams, we thought, okay, we need to move away from that. Another one is got, the quality's not great, but you can see it's got springs in every direction, it's got rollers all over the place, and it's just not something that we thought we were going to be able to produce and have it be underneath the 400 grams maximum limit. So again, here's another one right here. This was another idea that was put forward, but the problem is we've got incredibly small gears here, small pieces, and it just was going to be terribly, terribly hard to manufacture. So what we instead decided to do was think about using flexure springs. So what I've got right here in my hand is just a little piece of saw steel from the shop. So the idea behind it is, okay, if we treat it almost like a cantilever beam, granted it is bent, so the equations don't go completely, but it's close enough. If you apply a little bit of deflection here, it pushes force back down on there. And the reason we're talking about deflection here is because as the tape gets rolled up, it's going to make the diameter of the spool bigger, and so it's going to need to push back down. So as it says on the slide, the inner diameter increases by just about 4 millimeters, and to keep the boom from blooming, we need to supply about 20 newtons of force. So this is where we started to get into our initial design. So this was our first design. So it was going to require 6 additional pieces. The mass of the spring, so just the metal on the outside, was going to be 71.31 grams. And the total mass of this and the spool was going to be 186.95 grams. And the max stress that we had measured in it was 125,600 psi. The only disadvantage that we had to this design was it had way too much unused weight. So it's pretty ergonomical. It looks cool, kind of looks like something that you would see on a spacecraft if you're watching Star Trek. This is the missing piece that they need. But we just decided that it was too much weight not being used. And so here we have an example of it. This is using a program called ANSYS. For those of you ME seconds who haven't been introduced, you will be forcefully introduced very soon. So basically what we did here was we applied that 4 millimeter, 5 millimeter deflection to the ends of each of the rollers and just watched how the stress increased. So I'll show you how that ran. So what you're seeing here is, if you notice on the top left, it has that little color scale. At the top, the red is the maximum stress that is found in the element. The bottom is the blue. So we have a lot of blue here, which means that we have a lot of weight that's not really helping us support anything. And that's kind of an issue. We want to have, if we're putting something very valuable, very time consuming, a lot of time put into space, we want to make sure that it's as light as possible. Also, another reason why we want to make it as light as possible is for batteries, right? So we only have 10 cycles now, 10 cycles out, 10 cycles in that we have battery space for, but eventually we want to provide more. So if we can reduce their weight, there's more space for batteries, more time that it can operate. Okay, so our second design was going to require 8 additional pieces, and I'll show you the full design in a second, but I wanted to really zoom in on the arms. So the mass of each one of these spring arms is only 1.14 grams. So the total mass of these plus the spool was only going to be 117.92 grams. So the disadvantage though was it was pretty much too small to physically manufacture. So we have this saying in the engineering department of SolidWorks myopia, and what that is when you're working with a program like SolidWorks where you're drawing stuff out and you're extruding it, building it. The problem is since you can zoom in all the way, you kind of lose track of how small some things are. So on the screen, this looks like it could be a pretty big thing, but to give you a little bit of an idea, the thickness of this portion right here is 0.015 inches thick. So that's incredibly tiny. And then what we were trying to do from there was bend a piece of it, bore it out, drive rivets through it, and it didn't make sense with that type of small size to be even trying to get into something like that. So we threw that one to the side and moved on to our third design. So backing up. So this is what it was going to look like though. Basically what we had was we had it attached to the bottom and top. One thing that I didn't mention before is that these ThinSats on the edges have small holes in them. So you see right here, we've got basically screws to keep them in place on the top and on the bottom. Only issue was because of how we had the spool placed at this time, and also some of the equations we were using, it was really tough for us to try to get them directly across. So you can see this one I made a little bit more obvious because I wanted us to go and see what I was talking about. But they're not applying pressure at opposite ends of the spool, and that's important because if we're going to be applying pressure on the spool, we want it to be as evenly distributed as possible. Also, another thing with this and the previous design, if we look at the rollers on both of them are relatively small, and we didn't want to risk making the roller too small and not providing the proper force down across evenly, and maybe damaging the tape on the middle and having that wear down faster than the tape on the edges. So anyway, we moved on to our third design, design 3. So this was going to require 6 additional pieces. The mass of one spring, they're a little bit heavier, they're 3.79 grams, and the total mass was 123.21 grams. I was able to count that time. The max stress is 134,350 psi. So here's a little simulation that shows it going through all 5 millimeters of deflection. So as you can see in this, we've basically got a little bit of red going on near the throat, but because we had that long moment arm, it pretty much reduced it. And then also, in terms of blue, we've only got 2 parts that are really blue. We've got the base, which is very small, and then the connection piece. And that's more because just anytime you've got a connection like that, the inside part is going to be the one receiving most of the stress, not the outside. So this is how it would look, and as I mentioned before, the roller is the exact, or excuse me, not the exact, it's a little bit smaller, but it's a little bit smaller width than the spool, so that way we get that same force application across the entire width of the tape instead of it only pressing down to the center. Okay, so our final stats, the motor specs that we were able to get were 3 volts. So that should be 119 millimeters of torque available. The total mass added onto the ThinSats was 123.206 grams. So again, this is the total mass is like an apple and then like another slice. Think about how small that is. And then also it met all the mission requirements. So in conclusion, today I covered for you what is a ThinSat and why they're important. Talked about the ThinSat initiative and how we got our hands on this project. Went over the goals of the project, the design process that we went, and then I went over the final stats that we had. This concludes my brief. Are there any questions? Yes, sir.
Yeah, how did you